about that. Hello everyone, my name is Adam. I'm a professor at the Schulich School of Business. Really happy that you all came today. Let me introduce to you Dr. Rafid Mahmood. I've known Rafid for, what year is it, 2025? 8 years? 7? So Rafid did his undergraduate degree at University of Toronto in electrical engineering, a master's in the same discipline. And then he did a PhD with Tim Chan, who's sort of famous guy in the industrial engineering department there. I got to actually became one of the sort of supervisors of Rafid while he was there at Tim Chan. We've had several great papers together. After that, he went to NVIDIA, worked there, got extremely wealthy, and decided to take on a position as an assistant professor at the Telfair School of Business, which is at the University of Ottawa, where he does research in this sort of space of AI, machine learning, and operations research. Really interesting research. I think today you're going to hear a talk that is kind of in the intersection of operations management as well as deep learning. So thank you very much for attending.
Yeah, thank you. Thank you, Adam, for that. And thanks, everyone, for attending. You can guess from the title, right? The focus of this talk is going to be around the data aspect of building machine learning and deep learning models. So, in practice, when let's say a company or someone wants to build a machine learning technology or product, it usually operates along this process that's called an AI data flywheel. Right? So you start by collecting some training data. You need some data to build your model. Use this data to train and fit a machine learning model. And then once you've built this model, you have to go and validate how good this model is. Right? So this could be like you have some held out data to test it on some sort of performance metrics. This could be that you just give the model out to users, you deploy it, and you see how users interact with it. But you get some signal on where this model is strong, where it's weak, what we should do next, and you could use this information to then repeat this loop. So collect some more data, use this data to retrain your model, and just keep running along this flywheel. So it turns out that the data collection aspect of this whole pipeline ends up becoming one of the more expensive and certainly one of the most time-consuming aspects of the development of the machine learning product itself. So, for example, there's this survey, it's a few years old at this point, but this is of AI experts, stakeholders across a handful of different industries that all report that 96% of these enterprises that are trying to build AI models encounter some sort of a challenge with either the quality or the quantity of the training data that they're using. So this could be issues like there's bias in the data. This could be that there's just not enough data. This could be that the data needs to be annotated and we don't have the personnel or the technology to go and label this data. So there's a host of problems that come around with respect to data. Now, the focus of this talk is going to be on the second bar here. So I'm just kind of highlighting it, where 51% of these people who were surveyed report that they realized too late that they just didn't have enough training data in order to build the model that they needed to build. And so this is a bit of you can imagine if you're trying to build some sort of an ML product, this would be extremely disappointing, right? You spend all this time, you collect this data, you build your model, and then you're like, oh wait, I need more data, right? So now I need to redo this whole process again. So this is going to be what we talk about. So we can kind of just discuss a little bit why this is difficult, right? So why does this happen? Well, there's a few aspects to data collection. The first being that it's extremely time-consuming and it's expensive, right? We're using collection as this catch-all term, but data needs to be stored, it needs to be curated, it needs to be annotated, it needs to be cleaned to make sure that there's no noise and all these things. So, just to give an example, if you're thinking about autonomous vehicles, right, this is an exciting application of AI technology. In order to train an autonomous vehicle, in order to build these models, well, you need to have cars with all of these sensors driving around. Now, a car with a whole bunch of sensors could end up collecting over 1 terabyte of data per hour based off of all of the driving video and sensor information, right? And so, if you have 100,000 cars out on the roads that are all collecting data, this is a tremendous amount of data that needs to be processed and curated before it can be used. And then in a lot of cases, in addition to this curation, right, data needs to be labeled, oftentimes by humans. And often what you'll find is that there's entire companies that are focused around data labeling. There's companies that will have in-house data labeling teams, especially in applications where this labeling or this annotation requires expertise and skill, right? So for example, identifying major defects in silicon products and things like that, right? Now, an in-house data labeling team could end up costing a company somewhere around $40,000 to $50,000 per year. So this is kind of salary and technology and all of these things. So labeling is also an extremely expensive process. So data is time consuming, it's expensive. The other aspect of data that makes this challenging is that it's very heterogeneous, right? So you can kind of plot data along these axes of cost and on value. And in different segments, you have different types of data. So for example, a lot of this technology relies on handling what are called long tail or rare event or edge cases. You want to build a model that can detect when there's a stop sign. Well, your model has to be able to identify that the stop sign swinging out from a school bus is a stop sign, and it needs to know that the car needs to stop at this point, right? So this type of data is very valuable, it's super important, but it's so rare, and so it's going to be harder to find and collect. Now, on the other hand, you can also think about data that might be, let's say, less valuable per sample, but is also significantly cheaper, right? So the example of this is like synthetically generated data, right? A lot of AI products, especially when manual data collection is expensive, we rely on simulators, on synthetic data, on video games, things like that. This is extremely cheap, but then it might not be as valuable per sample. Like you might need 10 times or 100 times as much simulated and synthetic data in order to get the same type of a technology or model that you would with, let's say, just real manual collected data. So on this axis of cost and value, we can start to look at a few different objectives, and this is kind of going to be the focus of today's talk. The first half of this talk is going to be around this problem here, where let's say that I'm trying to build some machine learning model or some technology, and I need my model to get a certain minimum accuracy. So the example of this is, think about technology that already exists, but then we want to incorporate machine learning into it. So let's say, video conferencing technology, but we want to use AI to blur the background or change things. So in order for us to use or deploy this machine learning model on top of it, it needs to have some minimum performance. Otherwise, we're not going to use it, right? It doesn't make sense. So then how can I get this at the lowest possible cost? Get the model that I want while spending the least amount of money. Now, this kind of encapsulates a lot of these ML technologies, where ML is one part of a broader technology. We'll also talk about, in the second half of this talk, on a different scenario. And this we often see with things like large language models, where let's say that my company went out and bought a whole bunch of compute, like a massive data center, right? So now I have this resource. How do I, let's say, leverage this resource to the best of my ability and get the best possible model that can kind of achieve all the tasks that I wanted to achieve? So kind of two different ways to think about this: minimize cost while getting the best possible model, maximize the best possible model while kind of keeping all of my resources in check. So before we kind of go into this, I'll also just kind of briefly mention that this work that I'm going to cover kind of encompasses a broad literature space that's touched on by computer science, that's touched on by economics and operations, that's touched on by stats. So just kind of a few things to mention, right? A lot of this work that I'm going to be discussing touches on what are called scaling laws. So I'll be discussing more of this later, but this idea of how data and performance kind of scale. there's a rich CS literature as well on what's called active learning, where we want to know, given, let's say, resource constraints, how do I select data to get the best possible model? From the economics, from the operations, from the management side, there's a lot of literature around data sharing, data privacy, data pricing, data markets, right? If I'm trying to sell data or buy data, at what prices should I kind of go about this? And then also kind of mention that there's a lot of literature as well on a very relevant related problem in statistics around experiment design, right? So before we had predictive models, we had statistical experiments and scientific studies where also we have to figure out how do we get the people into our study pool, how do we figure out how best to design a statistical experiment or an analysis. Okay, so with all that said, the first half of this talk is going to focus on this one problem around how we can try and minimize the total cost of data collection in order to get the model that we want. So that first kind of setting that we talked about. And this is work that we've been kind of working on for a long while. This is with a lot of my colleagues at NVIDIA. And we had like some very early conference papers, and our journal paper just got published on this earlier this year. So what this work is going to focus on is basically understanding how much data I need to get some sort of a minimum level of performance. Now this is something that has been explored and tackled in practice a lot. So usually you have, let's say, an engineer who uses their judgment, right? Like, I've built a machine learning model before. I know that I needed this much data to build my model in the past. I'm dealing with this problem. I have some sort of a gut vibe that says that I'm going to need a certain amount. So you can kind of use past experience and past judgment. But that's not extremely principled, right? So what if you have to defend this position? So instead, something that is a little bit more principled, and what's a little bit more of a practical way to do this, is to leverage this notion of what's called a scaling law that says that the performance of your machine learning model scales with the size of your training data set according to this power law relationship. So you can plot on the x-axis the size of your data set, on the y-axis, let's say the accuracy of a classifier. You get this power law curve. And so what you can do is start by collecting a small pilot amount of data, just a tiny amount of data. Use this to understand how your model's performance kind of scales with this small amount of data. Estimate the relationship, this power law, and then use this to try and extrapolate. Well, if I need to get a certain performance requirement, where do I have to go? So very, very simple, right? Very practical. Anyone can do this, so this becomes a very standard approach. But there is some challenges with this approach. And so this is kind of coming from the danger of over or underestimation because of this power law relationship. So just to kind of give an example, let's say that I need to get certain performance. Let's say I need to get 67% accuracy, right? So I picked this number because it gives me nice round numbers for data set size. So this black curve is the real scaling law. And the ground truth basically says that to get 67% accuracy, I would need around 900,000 training samples. Okay, now let's say that I collected a small amount of data, and then I ran some pilot studies, I fit the scaling law, but I made a mistake, right? These are very notoriously difficult to get right? You have to kind of train these models appropriately at small scales. So let's say that I messed up and I got that orange curve, this curve that overestimates the scaling behavior. Now, if I were to use that orange curve to estimate how much data I would need, this would get me to collect 450,000 images. So basically half the actual amount of data that I need to collect, right? So imagine you get up to 450,000 images, you get a model that's like 57, 56% accuracy, and you say, okay, well, now I need to go and collect some more data, right? My project just got slowed down. So overestimating the scaling law leads to this large-scale underestimation. And you see the same problem again if you underestimate the scaling law. So if you get this blue curve, so it slightly underestimates, this would tell us that we need to go and collect 3 million images. So we could make a 300 times mistake, right? End up spending 3 times as much as we actually need, right? And then we build a model that has, let's say, 75, 76% accuracy, and we say, well, okay, well, we just wasted all this money that we didn't need to. So the core issue here ultimately is this notion of stochasticity in this scaling law estimation, which we want to try and mitigate. So how do we make better data decisions? Now, we'll model this as kind of a game. So let's say that we want to build this model with a certain performance. We're going to call this performance V star. And let's add another factor to this, which I mentioned earlier about this heterogeneity. Let's say that there's a bunch of different data vendors, right? Each data vendor can give us a different type of data. So one data vendor kind of gives us this long tail data. One data vendor gives us cheap synthetic data. One data vendor labels data cheaply. One data vendor labels data with more in a more expensive, but more rigorous way. And we can collect some initial data from all of these vendors. Now, let's also define a model performance function. So we're going to call this V of Q. So given a data set size, this is how our model is going to perform. And currently, it performs less than V star. So we're going to have to order some data. We can pay a certain cost from each vendor per sample. We pay this cost, we order this data, and then once this data comes in, we retrain our model. And then after retraining our model, if our model performance is still less than that target, V star, then we're going to have to play this game again. Well, we're going to have to order again, pay some more, and keep doing this. Now, we can't keep doing this forever. So at some point, we need to let out this product. So we're going to give ourselves a deadline. We're going to say that if we can't do this within T rounds of data collection, then we're going to terminate. And because we failed, we're also going to pay this penalty. Right? So this penalty is basically, imagine we couldn't build this model, right? We got delayed, we lost a whole bunch of revenue. So this is kind of the primitives of this game that we're going to set up, and this problem can basically be formalized into an optimization problem, where the variables to optimize are going to be this Q1, Q2, Q3, all the way to Qt. So the amount of data we should have at the end of each of these terms. And our objective is to minimize the cost of the additional data collected in the first round, Q1 minus Q2, plus conditioned on our model performance at the end of the first round being less than V star, the cost of the data collected in the second round, plus conditioned on the cost or the model being not good enough in the second round, the cost of the data collected in the third round, the fourth round, so on and so forth, all the way up until the final round. And if we still have not got the model that we want, well then the penalty as well on top of this. So this problem basically summarizes the game, just kind of puts it up into a big long optimization problem. Now, we can't solve this problem because to solve this problem, you need to know that V of Q function, right? And we do not observe this V of Q. This V of Q is basically that scaling law behavior. So we can only observe it insofar as the amount of data that we have. After that, we don't know what it looks like. So how are we going to solve this problem? Well, we're going to break it into 2 steps, right? So the first thing that we're going to do to try and reformulate and recharacterize this problem is we'll make an assumption that this V of Q is stochastic and that it is non-decreasing. So all that means is that no data is bad, right? More data is always good, and there's always going to be some randomness, right? So sometimes I will get some good data, sometimes I'll get not as good data, but it's all generally good. So if you make this assumption, then the problem actually becomes very straightforward conceptually. You want to collect just the exact minimum amount of data that you would need to reach that V star, right? Because you just want to get to the minimum, pay them the least, and then call it a day. And so we're going to call this the minimum data requirement, D star. And then you can basically show that the optimization problem is equivalent to the following form, where you minimize the cost of the additional data collected in each round times the condition that the data that you collected so far is less than this D star, right? And what you can show is that as long as your penalty is sufficiently high, then the optimal strategy is just to collect up to D star. So if your penalty is high, you collect up to that. If your penalty is low, then the optimal solution is basically to say, well, I shouldn't collect anything. I'll just take the penalty because that's cheaper than having to pay the money to actually build this model. Okay, so we can turn this into this function of D star, but D star is also something that's unknown, right? It's the minimum data requirement. To get D star, we need to know that scaling behavior. So how do we kind of deal with that? And this will take our second assumption, where we'll model this D star as another random variable with some unknown distribution, right? So it's got some probability distribution associated with it. And if you take this model, then you can take the expectation of that optimization problem, and essentially you can rewrite that optimization problem in the form of collecting the additional amount of data in each turn times the probability that the amount of data that you collected in the previous turn is less than D star, right? So turning everything kind of into this distributional form, right, where you're just looking at probabilities and risks now. And so all that's left is to estimate this distribution, right? So we can estimate this distribution essentially by fitting that neural scaling law estimator. So take some pilot data, fit a neural scaling law, and then you can just kind of bootstrap on that. So we actually do a very simple trick. If you sample, let's say, 3 or 4 different small data set sizes, bootstrap over those data set sizes, learn a distribution, pick whatever density estimation technique that we want to use, our favorite one, and then you get a distribution, and you can plug that distribution into this optimization problem, and then this optimization problem is actually very easy to solve. You just solve it with gradient descent, and you can just kind of plug and play it into any optimization solver, and it will spit you a solution. So this kind of summarizes the general algorithm that we're going to talk about, which is called learn, optimize, collect, right? So we start with some data, we have some target, some number of rounds, and then in each round, we estimate the distribution of this minimum data requirement using neural scaling laws. We solve that optimization problem, and then that tells us how much data we need to collect for this upcoming round. And so we just collect that amount of data. And then we see, okay, have we met the performance requirement? Have we collected enough data? If we have, good. If we haven't, then can we do this again? And if we can, then let's repeat this cycle again. But then the next round, just optimize for rather than 5 rounds, optimize for 4 rounds, optimize for 3 rounds, and so on and so forth. So any questions just before we move forward in terms of methodology or anything like that? And yeah, please feel free to ask any questions or stop me at any time.
So the monotonicity constraint was on the expectation or on the value?
The monotonicity constraint is just on that score function, on that model performance function V of Q. Yeah.
So if you have an instance where performance goes down with more data, is that a problem? Or like in a sample?
Mm-hmm. So like if performance goes down,
you made the assumption that performance will get better with data.
Mm-hmm, mm-hmm. Yeah. So when we model this, right, we always model it, let's say, with the power law. So in the case of the power law, that's not going to happen. If you make the assumption that if you break this assumption, right, if you say that like actually I'm going to try and permit this so that model performance does not necessarily continually increase with data, then what you would want to do is try and incorporate a different type of a scaling law. So in this case, rather than a power law, you could use some other different function. But then this becomes kind of a design choice that you have to use when solving this optimization problem. But under that assumption, if you break that assumption, then it's not always true that the minimum amount of data is the best amount of data, right? Because sometimes you'll get some more funky behavior. Yes?
So you choose to D star. So the first period is whatever, trying to get to V star.
Mm-hmm.
In the second period, if the realization of the state of the random variable is lower,
Yeah.
that's why you would have like a mix. Right?
Exactly, yes, if the realization is lower, yeah.
Is there any notion of, well, I've learned more about the problem because I've collected more data, so my estimate of V, the stochastic quantity, is like improved because of the additional data?
It's your estimate of D, the minimum amount needed, that's what will improve over time, absolutely. So
your estimate of D every round is actually
that gets updated every round, absolutely, yes.
But through F, right?
Through the F function, exactly, yeah.
So, but is there a notion of like, you know, if I have like a distribution robust optimization problem, right? The uncertainty set is decreasing every round because, or is that we just right now assume F is fixed into all rounds?
No. So because we're optimizing with this hat of this F hat, this estimate, right? So what you'll see empirically is that F hat is going to shrink over time. So just to kind of, if we pull back the scaling law, go back a little bit. So if you estimate at this point, you have this amount of data, you can imagine the confidence interval of your forecast kind of widening over time, right? But let's say that you, let's say you collect up to this point, right? Now you have information up to this point, so below there, you know everything. From that point on, there is a new smaller confidence interval that starts. So at this 900,000 regime, the width of that confidence interval has now decreased. And so that's kind of like the level of uncertainty that you're dealing with.
You were talking about data sets that contain synthetic data as well, which may mean that the first 60–70% is garbage, and then after you collect some more, the data that is harder to get to.
Yeah.
So basically, the power law looks.
Oh yeah, the power law can have like
and
can
fine.
be more
Everything,
steep.
everything
Yeah.
still works even if it's.
Yeah. As long as you have that monotonicity assumption, right? The nature of the power law doesn't really matter, right? Like it'll work regardless, yeah. Okay. So I will mention very briefly, just kind of in one slide, there's a lot of math that we kind of did with this work, which I think is not super important, but I think one interesting setting to talk about is what's called this one round, one vendor case, right? So think of this as, let's say my company wants to, they want to build some ML technology, but they just need a one round estimate, right? I haven't done anything, I just want to know how much is this going to cost, give me a forecast. So what turns out is that this problem is actually becomes very similar to a classic problem in operations management. It's called the news vendor problem, right? So the idea of the news vendor problem is basically you're selling something. Let's say you're selling newspapers every day. Now today there's going to be 100 people that want to buy the newspaper. If I sell less or if I produce less, then I'm not meeting demand, right? And I'm losing some opportunity. If I produce more, then I'm overproducing and I'm paying too much. And so this one round setting essentially becomes very similar to that news vendor problem, where you can think of data as an inventory. I need to collect data. There's some unknown demand, which is this D star, the minimum amount of data that I need. And if I collect more than that D star, then I'm paying this cost of over collection. If I'm collecting less, then I'm paying some penalty and I'm paying some loss for that. And what you can show is essentially this problem has a very simple, intuitive theoretical result, which is to basically say that under some assumptions on the cost and the penalty values, the optimal solution for this, or the optimal strategy, is to basically define an acceptable risk. So there's some acceptable risk parameter, epsilon, which is a function of this cost and the penalty. And the optimal strategy is essentially to just collect up to the 1 minus epsilon quantile of that distribution of D star. So if you need to make a one round estimate of how much data do I need in order to build this model, the way I should think about this problem is to say that I am willing to accept, let's say, a 5% chance that I under collect and I mess this whole thing up. And if I if I'm willing to accept this 5% risk of failure, well then, based on my distributional estimate of this D star, what is the 1 minus epsilon quantile? What is the 95th percentile that I should collect? So very simple kind of one-round strategies that are very conservative and can help you mitigate risk. So,
Sorry, so
yeah.
what's the detailed analogy to the news vendor problem? So the penalty P is not providing enough supply?
So you can think of the penalty P as being a penalty for not providing enough supply. So D star is the unknown demand for data, right? And if you don't meet that demand, then you pay this penalty. So if I didn't meet all of the demand for selling all these newspapers, well then my shop is going to get run out of town. But if I overproduce, well then I'm left with a bunch of extra newspapers. Yeah. Okay, so that's all I'll kind of say in terms of theory. I'll just talk very briefly about some of the numerical analysis that we did, because we tested this very extensively on a lot of computer vision data sets. So all the kind of classical computer vision problems, right? So classification, detection, segmentation, and for everything, we swept a whole bunch of parameters, right? So we swept the number of rounds, we swept different performance requirements, and then we kind of averaged out all of the results on all the settings. And we compare against just that power law estimation, so just against the estimating a scaling law and using that strategy. And we evaluate on a bunch of these aggregate metrics. So there's the two metrics that we're going to evaluate on is what's called failure rate. How often do we fail to meet that unknown demand? How often are we under collecting data, right? So if you think back when I opened this, we said that 51% of the time these enterprises under collect data. And then we'll also evaluate on cost ratio. So let's say that we collected enough data. How much are we spending? Are we spending 5 times the minimum amount that we needed to spend? Are we spending 500%, or are we spending just a little bit more than what we needed to spend? So there's a whole bunch of experiments. So there's this big table here. These are all essentially what are called these single data vendor problems. So just one type of data. So not dealing with a lot of different types of data. 1 round, 3 rounds, 5 rounds of data collection. And then we have classification, segmentation, detection problems. So what I want to kind of draw your attention to is a few things. So the first thing that I want to draw your attention to is these 2 columns that represent the failure rate if you are using just a scaling law estimator, and if you're using our strategy, this optimization. And what you show is that our strategy consistently has a lower failure rate. So more often than not, we are collecting enough data in order to build this model. Now, more than that, our failure rate is consistently less than 5%, especially if you're giving multiple rounds of data collection. So this is important, right? If you're just giving 1 round of data collection, there's a lot of risk you're taking. You're very likely to kind of mess things up. But if you permit yourself a budget and say, I'm gonna give myself the time to collect 3 times, well then our failure rate is consistently less than 5% on all of these settings. So we're very comfortable about being able to get enough data. And we also do this very parsimoniously as well, right? So we're doing this without spending a ridiculous amount, right? We're not spending 3 times the amount of data that we actually needed, right? We're spending somewhere between 1 to 1.5 times the amount of data. So we're collecting just enough data to meet these data requirements. Now, all of this is this single vendor scenario. I'll show one example of something where you have multiple vendors, and we can think of this in kind of a long tail setting. So imagine that we have, we're dealing with this massive classification problem. This is just on the CIFAR 100 data set. It's a classification data set with 100 classes. And let's say that some of the data is this long tail data. It's very expensive. The other half of the data is common data. It's very, very cheap. So it's an order of magnitude cheaper than the long tail data, right? Now, we can choose to collect common data, or we could choose to collect long tail data. How do we kind of balance these 2 different data sources when we're building our model?
So you're just simulating this, there's nothing...
Exactly, yeah, I'm just simulating this. This is nice because I already have the data, so I can kind of simulate just how much I'm paying in terms of long tail versus common. And the story that you get is very much the same thing. So our failure rates consistently lower, and interestingly, our cost ratios are also very, very parsimonious. I think one thing that's very interesting is that sometimes our cost ratios are lower than the cost ratios if you're just using the estimator itself, the estimator only strategy. What this basically means is that when you're estimating and you have to juggle, let's say, 2 or 3 different data sources and data vendors, trying to work out how much data from each of these different scaling laws kind of compounds on your risk because of all of the uncertainty now from like multiple decision variables that you have to kind of play with. Whereas our strategy is a little bit more robust and parsimonious. I'll show, in the interest, okay, no, I'll show one last result kind of on this. So you can also kind of use this to do a lot of very interesting, specific question answering. So something you can think of is like, let's say that I've already deployed my model and then I found a new test case or a new edge case, right, where my model is not performing, right? So I just need to get the data to patch my model up, right? How much data do I need of this new class that I'm playing with? So again, we kind of simulate this with this with the CIFAR 100 data set. We train a model on like 99 classes. We try to figure out how much data we need on the 100th class. And then again, the story is very much the same as before, right? Consistently lower failure rates, consistently lower costs as well. So this is just kind of a sample of some of the experiments we ran. We ran a whole bunch of different experiments and testing different things out, and we kind of get the same story over and over again. So just the kind of the key takeaways from all of this, right? I want to kind of take away. I want you to kind of take away from this idea of thinking about data collection as an optimization problem, right? You have a bunch of these different data variables. How do we kind of manage all of these decisions in a nice strategic way? And what's nice about our strategy is that it's kind of shown this very consistent improvement in terms of a 2x improvement, especially in terms of failure rates and sometimes in terms of costs. And what's nice about this framework of optimization is that it allows us to kind of answer more of these kind of custom modeling choices, right? So, you know, a question like, how do I get enough data for just one class? Or how do I kind of evaluate different data collection strategies? All of those can kind of be modeled in this nice general framework that we have here. So that's what I have for kind of the first talk, but I'm happy to take questions. Yes?
Yeah, just totally out if you want to get to something else, but I just want to see if I could understand. So in your modeling of F,
yeah,
you said you could use any density estimator.
Mm-hmm.
So what are you using?
We use, for the single variable ones, I used the kernel density estimation. And then for the multivariable ones, I used Gaussian mixture models just because it's easier to get gradients.
So I guess my question is how much of your advantage stems from the restrictive assumption of this power law in your control versus this non-parametric approach to modeling F?
Oh, yes, that's a good question. So we ran some experiments on this, on like what happens if you, let's say, don't optimize, but you just estimate with the distribution. I haven't presented these results, but that basically gives us, part of the way. So just using, let's say, a density estimator, that gets you an improvement, and then the optimization gets you an additional improvement on top of that. Yeah. Yeah.
Is there any notion of like, you just can't achieve V-star?
We didn't test this out because it's a bit of a degenerate numerical setup.
I know. I just asked. We actually had an issue that's like I don't think we're ever going to get to maybe the predictive accuracy of ROC or AOC that we want.
Yeah.
But I'm obviously it's out of scope.
So
there is this notion of like, okay, it's attainable.
Yeah. So that is an assumption. So that's a very good point. It's an assumption that we make that V-star is attainable for all of this to work, right? I think like in practice, of course, it may be that V-star is not attainable. This becomes a question now of the other levers that we have at play, which is not just data, but also model design, for example. So you can think of, let's say, if you have a small pilot data set, you can see how scaling behaves with certain model choices that you make versus other model choices that you make. So for example, like certain model architectures like transformers have like very nice downstream scaling behaviors, right, that you might not see at kind of small data regimes. But you can still track the scaling aspect and then kind of optimize your model choices to try and get to the V stars that you want. Yeah. Yeah.
So often it's not a matter of how many rows, it's a matter of which columns you collect, right?
Yes.
So if you collect irrelevant variables,
yeah,
large, you won't see any scaling.
Yes, yes.
Have you consider this feature selection problem as well?
Like the idea of like this the heterogeneity of data where you're.
I need this column that I can get. That's what we had in the project, right?
Mm-hmm.
We wanted demographics.
Mm-hmm.
We cannot get them from the.
Oh, I see. That's a good question.
So it doesn't matter how many rows.
Yeah. I see. That's a very good question. We have not studied that in this work, but this kind of ties. It's similar to the aspect of data vendors, right, or data mixtures. There are ways to kind of optimize around that, but I think it's not like an immediate extension.
Discuss it.
Yeah. Happy to discuss it offline. How strict are we in terms of 3 o'clock?
We're okay to go over if you need to.
Just a few minutes, or
Yeah.
Okay. So I won't show all of the results and everything here. But I wanted to kind of emphasize this was like the first bit in a much broader research stream. And so this is kind of one of the follow-up works that came out of this, right? So this is a collaboration with a handful of folks from all over the place. Primarily, I'll give credit to Fei Yang, the first picture that you have. He was a PhD student at Virginia Tech who did basically all the work for this. But this looks at the kind of a problem of trying to look at how do you do data collection for large language models, where the problem dynamics are a little bit different. So different in what way? Well, there's a few things that make LLMs more challenging. First, LLM training is expensive, right? So we're now thinking about building models that cost, let's say, $10 billion, $100 billions of dollars in terms of compute and resources and all of this. So the question is no longer how do I minimize cost to get the model that I want? It's more I have to pay this cost in terms of building a data center. How do I get the best model, right? How do I use this resource the best I can? So training is expensive, and data is also very heterogeneous, right? So we're no longer thinking about one type of data or maybe like one or two different types of data, right? To train an LLM, you need this is a bit outdated, but you need data that's like code, you need data that's research papers, you need data that's like patents, Wikipedia, different languages. The amount of different types of data basically explodes. So the way to think about data collection for these problems now is slightly different, but it's more as a data mixture. So you can think of this like you have a bunch of different data domains, same thing kind of as a vendor, but just using a slightly different terminology. And in these settings, it's not about collecting the data. The data is available on the web. We have all the data that we could possibly need, right? But some of it is good, some of it is bad, some of it is more or less useful. Instead, what we have is a budget, right? That says we can collect a certain fraction, we can use a certain fraction of data from each of these domains in order to train our model, right? So given our budget, we'll spend 30% of it on code data, we'll spend 40% of it on Wikipedia data, we'll spend 10% of it on archive data, and so on. And we want to make sure that our model is good for all of these tasks, right? It needs to be able to parse code, it needs to be able to deal with science, it needs to be able to deal with reasoning and all of that. And so our goal is to try and select weights on each of these domains that define a mixture of what percentage of our data should come from each of these domains that's going to maximize performance on all of these domains altogether. Now, this optimization problem is significantly harder as well for two reasons. So the first being that when you have all of these domains, you start to see an interaction effect where data from one domain may be useful. So maybe kind of collecting code data is going to help me parse, archive, and research papers. Collecting research papers data is going to help me on all of these tasks. Collecting data on, let's say, product reviews is not going to help me in answering questions around code. Now, in addition to that, there's also a quality and quantity trade-off. So this is kind of from a paper that was published last year. That kind of shows that, well, if you rank data on quality, so you have high quality all the way down to low quality data, if you have a specific compute budget at the small budget, it's strategic to just use only the best data and just show that data over and over again for training. But if you have a large compute budget, then it's actually strategic to make your data set more diverse, right? Show some of the high quality data, but also show some low quality data as well, rather than just repeating the same data over and over and over again. So we have to kind of now balance these interactions as well as the fact that you have a quality and quantity trade-off that can be completely different based on what budget you have. So at a small budget, some data sets might be more valuable. At a large budget, the makeup of your data set could be completely different. Now, we tackle this problem in two steps. The first being this observation where if you fix the budget, then the performance on these domains actually follows a scaling law. So you can think of, let's say, the performance on a specific domain, so on code, for a fixed budget, is going to be proportional to the amount of the budget that is allocated to that specific data, so on coding data, plus this constant that we call the effective data set size. So this is some fixed value that represents basically how much contribution other data sets or other domains are bringing to this. And then all of this to a power law exponent. So essentially, the amount of data that we have from this domain, that's the variable that we can control. And these two things are just constants for a given budget that we need to be able to estimate. And so we can always estimate this again, kind of using that same idea of taking some small pilot data, kind of fitting the scaling law and then figuring this out. But this gives a simple strategy. If we know what the budget is, then we can estimate the parameters, solve the optimization problem, right? That's easy peasy. But the catch here is that estimating these parameters is now actually quite difficult when we're dealing with large data budgets, right? So at a small budget, we have a small amount of data, let's say 300,000 tokens. We can kind of fiddle around with this, run some pilot studies. But then how does this look when we're going to, let's say, 3 billion tokens or 1 billion token or 60 billion tokens? Well, at that massive budget, we don't have the resources to just run a bunch of these pilot studies. It becomes extremely slow and expensive. So what we need to do then is to use the second observation that we have, which is that the data mixture weights themselves actually scale proportional to the budget as well. So this is kind of our second observation here, that at a very small data budget, right, you have this makeup of your data set, but then as you increase the budget, and this is on a log-log scale, the proportion of data from each of these domains will also scale linearly. And so this gives us kind of a tool to leverage with, where if we can estimate this scaling behavior on top of the initial scaling behavior, so not just how the mixture scales, but also how the budget scale, then we can work out at a high budget how much data we need. And so this is our strategy that we call auto scale, or automatic scaling of data mixtures. We start by sampling a small budget and then running this pipeline where we fit the scaling laws for the specific weights. We solve the optimization problem that we call direct data optimization. So that's that optimization problem at a fixed budget. And then we do this once, we do this twice, maybe we do this 2 or 3 times, right? And this gives us a few sample points at a few small budgets. And then once we have that, we can then track that second order scaling behavior on how these budget weights are scaling as you increase the budget. And this gives us what we call auto scale, where we follow along this second level of scaling to solve the optimization problem of, at a high budget, what should our data mixture really be? So I will just show two quick results before wrapping all of this up. Right, so we use this framework to optimize the training of a GPT-2 model. Right, so nowadays kind of quaint, but we use this data set, the Red Pajama data set. It's got a bunch of different domains. It's got 1.2 billion tokens. We want to figure out what is the optimal mixture of data from this data set. And we evaluate on perplexity, so just a notion of like what is the correct token probability error averaged over all of the domains. And so this is what it kind of looks like. On the y-axis, we have the perplexity on average over all of these domains. On the x-axis, what we have is the amount of training compute that was spent, right? So the training time and compute that was spent there. And this thick red line, this is our auto-scale strategy that basically says, at each of these budgets, what should our data mixture be? And then the other lines are other different techniques for working out data mixtures. And the key thing that I want you to kind of take away from this is this idea that auto-scale, our approach, is consistently getting us the same performance as these baselines, but significantly faster with significantly less compute time and energy that's spent, right? So somewhere between 28 to 38% less training time is needed in order to get to the models that we want, the performance that we want. So this way we can save a lot on resources in terms of compute costs and things like that. And then what's nice is that this is also kind of averaged over all of the domains. This table just kind of shows each of the individual domains. The key thing that I want your attention to draw your attention to is the worst domain, right? So all of these different methods that exist from the literature, all of these methods, they all kind of struggle on the C4 domain, right? So this is kind of a large web domain, a large web data set, and it turns out that autoscale also struggles on it, but our performance on the worst domain is significantly better than all of these baselines. So the way that we're getting this performance improvement is really by identifying the worst performing domain and really pushing down error on that domain as well. So we have a nice little empirically observed robustness to the strategy. So that's all I'll show in terms of numerical results. So just kind of to wrap all of this up, key takeaways from all of this. What I want to draw your attention to is how different the optimization problem becomes from the first half of this talk that we looked at, right? Where we're dealing with a bunch of these domains, a bunch of these data sources. This optimization problem becomes a lot more complex. And the clear example of this where we test is LLMs, but you see this in robotics, you see this in autonomous vehicles, and in many other settings as well, where there's a diversity of tasks and domains to deal with. And then within this, the key thing to note is that the optimal data mixture itself differs across compute budgets. This is a very classic pitfall that people will often make, where I start at a small budget, I figure out what is the data mixture, and I find out, okay, well, this data set and this data set is the most important. Now let's scale this up. Well, then it turns out that you actually messed up, right? There's other data sets at a higher budget that are more important and more relevant, that could have gotten you the same performance. So naively just scaling data set size is in itself a pitfall and a trap, right? And in this way, our strategy is nice in terms of tracking how the domain importance kind of scales over time, and this kind of leads to a nice compute efficiency, especially over baselines. And this is kind of important because, well, nowadays frontier foundation models cost a tremendous amount of money in order to build and design. So just to kind of wrap things up, and then happy to take more questions, but basically just to summarize, right, I want to emphasize some of these things, that data purchasing and mixing decisions, right, a lot of this is kind of done with empirical judgment, kind of taking this all the way back to that first half where engineers and enterprises kind of make these eyeball decisions or past experience to guide how much data they need. And this can lead to a lot of potential pitfalls and errors, right? And this becomes increasingly important, especially as we're dealing with things like LLMs, where the cost of designing models is now more and more expensive, and we need to deal with things like volume and mixture and model size and what have you. Right? This also has a lot of downstream impacts as well. Some things that I haven't talked about, but we have some work on some of these, right? So on things like energy, on sustainability, on the pricing of these LLM models, where can we build cheaper or more expensive deployments to users. Now, two kind of further questions, just to kind of highlight the things that we are that we're working on here and there. One being what to do when data domains and data vendors are not well defined. This is very common in things like robotics or in autonomous vehicles, where the tasks and the domains are very continuous, right? Rather than for LLMs where the domains are very, very discrete. Coding, writing, math are very, very explicit. If you're dealing with robot interactions, all of the different tasks that you're dealing with kind of blend into one another. So there, you need to be able to learn the different domains themselves before you can try and optimize a data mixture. But that can give you nice performance improvements as well. And then the other thing that I think is quite interesting and important to note is the impact of all of this on users as well, right? So we're pushing all of these resources on trying to get the best possible model, from going from 80 to 85% accuracy, from 85 to 86% accuracy. But because of scaling, it's harder and harder to get more and more marginal gains. Now, is that actually important? Is a second important question that we should actually think about, right? Does the user perceive value in us going from 85 to 86% accuracy? Is the potential revenue that we gain from deploying this model and getting users to use a better model, does that offset the actual costs of pushing the model further and further? So when is the optimal time even to kind of stop pumping our model and to kind of move on to other projects and things like that? So with that being said, I'll end it just 2 minutes over time. Thank you all for listening. I'm happy to answer any questions, and then all of this work is based around a handful of papers. The first one's kind of was in NeurIPS and J. Millar, and then the more recent one was published in Colm earlier this year. And then thank you, of course, to all of my wonderful collaborators on some of these works. Yes?
That was really interesting, thank you. I have a kind of a general question, which is if you have anything to say about the origin of these scaling laws in these problems, and in particular, especially your second order scaling, right?
Mm-hmm.
So do you have any conjectures about why these hyperparameters scale? Or is it just an empirical, I shouldn't say just, but is it an empirical observation?
I see. Yeah. So there's a rich history of scaling laws. I would say a lot of the early works around this is even from the 90s on learning curves, which is more often spent on kind of more classical ML models. But you see different scaling behaviors there, right? So it might not be a power law, it might be different functions, but you see some sort of a similar same idea there being kind of this concave nature where marginal improvements are harder and harder and harder to get. In terms of theoretical or less empirical observations, there's a lot of connections towards like generalization bounds and generalization theory. So I know that there have been works to try and develop theoretical bases for these scaling laws. There's always this kind of like exponent related generalization bound or scaling behavior. So I don't know what is the current state of the literature on this, but I do know there was at least a few papers published over the last few years on theoretical guarantees or theoretical bounds or explaining these neural scaling laws from a theoretical basis. Yeah.
It's a bit related to convergence rates, like things like CLT.
Yes, exactly. Yeah.
Estimate something that the 91st.
Exactly. Yeah.
As meaningful or needed to get the estimate of the average population or whatever it is.
Yeah.
So related issue is that, like in performance critical applications, you mentioned autonomous driving. So power laws are bad, right? Because they're very heavy tables.
Yeah.
And so usually in traditional engineering, usually we have redundant systems where we hope are somewhat independent. And so we kind of solve this the long tail problem. And that seems like a challenge in the setting because you're kind of assuming, although you kind of have an adaptive method, you're kind of there's an underlying assumption of a continuous, predictable function, right? Whereas in traditional engineering, we kind of say, I'm going to try to choose very different systems and cascade them.
Yes, yes.
So, do you have any comment on that?
So the effectiveness of scaling laws, the one of the things that we make an assumption here, right, which may differ in the practical setting, is the correctness of the evaluation criteria, right? So in order for all of this to work, right, we've made this assumption that we have a gold standard way to evaluate model quality, and that gold standard way to evaluate model quality has not changed, right? But when you're engineering some sort of a product, especially something that goes into the wild, you start with one notion of like model quality, and that in itself is going to change over time, right? I'm building a robot. I expect this robot to kind of operate inside specific square rooms, right? And then suddenly I let my robot kind of hang out outside, right, on a hallway, or I introduce a furniture in this room, or I introduce something into this room. So in real life, all of these things kind of change, and this is going to change the scaling law as well. So that is something that you kind of have to factor in, which is this notion of having to continually update your scaling laws and your distributions and all of this. So we do a bit of this in this work. So every time you get to kind of reevaluate and re-update. But you could run into kind of a perpetual chase of just kind of continually chasing improvements because your evaluation criteria are also changing over time.
Hi, thanks so much for the talk. I'm not a computer scientist, so this is more of I'm coming from a social science perspective. So, especially in the first study, you're talking a lot about accuracy and when you do more data collection, when it's realized that there's failure going on. Do you find that certain types of questions end up requiring more data collection to answer? So, like, are you finding that trying to identify accuracy in images for certain types of things end up like with that 5-round collection, whereas other things you're like more consistently seeing 1 round? You know what I'm saying?
I see, okay. So in terms of, obviously for different tasks, you're gonna see completely different scaling laws, and this is important, right? So for example, if I spend all my time doing medical imaging, and I understand the scaling laws there, and I suddenly go over to like robotics or autonomous vehicles, the scaling laws are completely different. So my expertise here is not gonna help over there. In terms of the performance of our strategy, in terms of the number of rounds over different tasks, that's an interesting question. We haven't explored whether our strategy is particularly strong or particularly weak based on the domain, because mainly we just work on very, very general, all the experiments are kind of on very general computer vision data sets, but that would be something very interesting to explore, the robustness to different domains where, let's say the scaling laws are not as pronounced or have more interesting idiosyncrasies.
I'm especially interested in how we get to answers to these tough questions, and it's interesting to hear that sometimes you need 5 rounds, maybe you need more, sometimes 1. So you had pictures of chairs, right, in your early examples, but I imagine like nonverbal cues from the face. I wonder if that's more of a 5-round type thing versus a chair as a 1-round.
It's certainly like more data that you need, right? So I think that like if you need more data, so let's say the task is harder and you need more data, then you're opening yourself up to more risk of error, like errors in your estimates, right? If the actual amount of data that you need is somewhere between like 5 to 20 versus if it's like between 5,000 to 20,000, right? You're more likely to make a mistake on that setting than you are to make in a smaller setting.
I think like, I'm want to ask like a kind of similar question, but like from a slightly different viewpoint. So like also referring to the first part of your talk. So you've got a model that works reasonably well, so you've collected lots of data, but now you are looking at like fringe cases, edge cases that are not captured well, and you figure you don't have enough training samples on the long tail end somewhere, and you augment your training data
Yes.
by that. Which means that, of course, those cases you are interested in because they are rare cases, but now you are sampling those training data for those cases explicitly, which means that you are changing your overall distribution.
Yes.
And in some cases that might be wise. So for discriminative models, you work, say like medical imaging or something, you might want to overrepresent those cases. But for generative models, you may not want that, because you want like a representative distribution of your training data, so that you don't change priors and biases. So how would you deal with that?
So that's a very important problem. I think like as you add more and more precise data decisions, so this edge case, this error, this failure mode, this setting, you're moving more and more into that heterogeneous setting where you have data mixtures that you're dealing with. So as the heterogeneity of the data increases, I think the second half of this talk is more applicable, where what you need to optimize is a mixture of data, right? Where you want a certain amount of data from each of these specific domains, these failure cases and so on, but you don't want that to like overpower the rest of your data set, right? Because otherwise, what will happen is that you could end up forgetting things or introducing more errors, right? So you build this product, you find some error, you try and address this error, you keep doing this for like 4 or 5 or 6 different errors, and then at some point you realize there's like errors that didn't exist way back when 6 months ago that are now errors here, right? So the only way to kind of track that is to keep track of all of these errors or these potential failure scenarios and understand what is the mixture of data to try and optimize.
I mean, that of course, like you would try to find a trade-off between those two things. But aren't there architectures or ways to keep track of 2 different distributions in a way? So like one would be really the prior distribution of events out in the world, and the other one would be a label that you apply to each data point in your training set that expresses the importance or something, so that you can keep really the natural representative distribution of event frequencies apart or separate from the significance that individual samples have. That makes sense?
Yeah. So I mean, there's a lot of machinery that you can start to use, right? So if you want to use like specific algorithms, specific modeling techniques in order to handle these long tail scenarios, right? So you want to use something like importance sampling or whatever. That is totally doable. What will happen is that will change the scaling laws itself, right? So that's the other lever that we have in play, right? So if you fix all things, so algorithms, compute, everything else, and just work on data, then you have one machinery here. As soon as you introduce this other lever, the scaling laws as well will change. So it might be that like with a specific technique, if you want to do like some sort of like repeat factor sampling or importance sampling or whatever, then you might not need the heterogeneity. That is certainly possible. Maybe then you can just kind of optimize for under that algorithmic assumption and find like nice clean scaling laws. It's just certainly possible. Yes.
Very nice talk, thanks. I have the same question that was answered. So you are choosing, let's say, the percentage of data to the east of me. What if in the situation we don't have enough data, and a lot of times we don't have enough labeled data, what's your insight? How do we get it through the use synthetic data? And if we as a generate data from the existing data. What's your insight? How do we do it?
Right. So I didn't show this experiment, but we run this in our paper where we look at, let's say, semi-supervised learning, right? So imagine we want to build this model. We don't have all of the labeled data, or labeled data is expensive, but then unlabeled data is plentiful and it's cheaper, right? You can think of this kind of using the machinery that we talked about in the first half of this talk as there being two data vendors, right? Unlabeled data being cheap, labeled data being expensive. There is a scaling law in the full two-stage algorithm where you use, let's say, unsupervised learning or self-supervised learning, and then you use supervised learning, right? There is a scaling law there. But if you have these two data domains, then you can kind of fit the corresponding scaling law and then try and optimize how much data from each of these domains to collect. And usually it's like, oftentimes it's, for example, like let's say like 10 to 1 or 5 to 1 or something like that.
So to get to pay for the more data instead of generating synthetic data, right?
There's some trade-off basically, right? Where synthetic data can like get you a significant performance boost, but like, for example, the way to think of it is like synthetic data or unlabeled data or kind of lower quality data, that might get you a lot of value to get up to like, let's say 70% accuracy, right? But then pushing from 70 to 90, it's just like way too hard because the value of this data is like not that good at that marginal level, right? So to get to 70% accuracy, just use only like cheap data. But then if your goal is to get to 90% accuracy, then you're gonna need to have to spend some more to get your model a little bit better.